Hello friends, today we are going to study one of the most important concept of geometrical optics, that is Huygen's eyepiece, which is often asked in exams. So without wasting a single second, let's try to understand it. So firstly I am telling you what is eyepiece. Actually eyepiece is a lens or a combination of lens that is used in an optical instrument like telescope or microscope through which eyes views the image found by the objective lens. You have studied in your previous classes that in a telescope or in a microscope there are two types of lenses, eyepiece lens and objective lens. The one which is closer to the eye, that is called the eyepiece lens, and now the eyepiece lens also a combination of two lenses, that is field lens and eye lens. The one is more closer to the eye, that is eye lens, and that is far from the eye, that is field lens. So now this eyepiece is given by Huygen, so it is known as Huygen's eyepiece, and the specification of this eyepiece is that it is devised to remove the chromatic or spherical aberration from the complete system. Now if you don't know what is spherical and chromatic aberration, so you have to watch my previous video, then go and watch. So here as you can see, in an Huygen eyepiece there are combination of two lenses, eye lens and field lens, and both are plano-convex lenses. That is, the one surface of the lens is plane and the other one is curved, and both the surfaces are curved outside. That is convex lens, convex surfaces you can also call it. And it is also to be remembered that the focal length of the field lens is 3 times the focal length of the eye lens in this case, in the case of Huygen's eyepiece. So now if you consider that f1 is the focal length of the field lens and f2 is the focal length of eyepiece lens, then you can say that f1 is equal to 3f2. And the arrangement of this combination is made so that the separation between these two lenses is equal to the twice the focal length of the eye lens. It means, as you can see, that if the focal length, we consider that focal length eyepiece of the focal length of eye lens is f, then the distance between these two lenses or separation between these two lenses is 2f, f plus f 2f. Now as we can see that f2 is the smallest one, so we consider that let f2 is equal to small f, and then f1 will be equal to 3f, and the distance of separation between both the lenses will be 2f. Alright, so it is the arrangement of the diagram. Now I will tell you the working. So the working of Huygen's eyepiece is shown in the figure, as you can see that. So the light rays incident from outside are meeting at eye dash. As you can see that these are the two incident rays that are meeting at eye dash. If in the absence of this plane surface, if these two rays incident on the curved surface, so in the absence of the plane surface, they will make an image at this point at eye dash. So you can say that eye dash is the virtual object for the eye lens, or you can say that eyepiece lens. Actually yes, this image or this eye dash point, the image found at the eye dash point is the virtual image for this combination, for virtual object for this combination. Now after passing through this whole lens, the two rays will meet at the point I double dash. So you can say that the image found by the field lens is at point I double dash, and this point is just between the both the lenses. And now the final image will formed at infinity by the whole eyepiece. As you can see, this ray will go from here, and now this ray will incident here and bend. So these two rays will be go parallel, and the image formed at infinity. And it is also essential that image formed at point I double dash should be at the focus of the eye lens. That is, the distance of this point is equal to the focal length of the eye lens. And as we have considered the arrangement in such a way that the distance between both the lenses is equal to the sum of two focal lengths of the eye lens, so the distance of this point I double dash will also equal to the focal length of the eye lens with field length also. So now as we have considered that it is at distance f from the field length also, so it is the image formed by the field length, so we can consider that v is equal to f. I hope you get this point. The image found by the field length is equal to the focal length of the eye lens. The distance is also the same, that is f. So we know that we denote the distance of image from the lens by v. So here v is equal to f, and focal length of the field lens is equal to the 3f, f1 is equal to 3f, and we know the lens formula, that is 1 by f is equal to 1 by v minus 1 by u. So in this case, as the focal length is equal to 3f and our v is equal to f and minus 1 by u. So by this equation we will calculate u. 1 by u is equal to 1 by f minus 1 upon 3f, that is equal to 2 upon 3f. So u is equal to 3f by 2, that is the distance of the object from the field length should be 3f by 2. And here in this combination, I dash is acting as a virtual object, so the distance of I dash should be 3f by 2 from the field length. So now we will study or understand the position of cross wires. So what is cross wires? So actually cross wire are two thin wires that are perpendicular to each other, and it is used to measure the distance between the two particular points of an object. Although it is not important, but the cross wire generally should be at the position of I dash in the Huygen's eyepiece, but due to some mechanical difficulties it is not used in the Huygen's eyepiece. So you can also write or not. If you want, you can write that the position of cross wire can be at point I dash, and it is not used in Huygen's eyepiece. Now the condition for achromatism. So for achromatism, the separation between the two lenses should be equal to the mean of the focal lenses. The distance of separation between the two lenses must be equal to the mean of the two focal length, that is f1 plus f2 upon 2. So in our case, f1 is equal to 3f and f2 is equal to f, so we can write it like that. So here 2f, the required distance between the both the lenses must be 2f, that is in our case actual distance. We have taken already the distance between the distance of separation between the two lenses, we have taken it 2f. So d required is equal to d actual, and by this condition the achromatism would be satisfied. Now condition for minimum spherical aberration. So to obtain the minimum spherical aberration, the distance of separation between the both the lenses is equal to the difference of the focal length of the two lenses, that is f2 minus f1, and in our case it is f2 is equal to 3f. So sorry, it was a mistake. So here f1 minus f2, and f1 is 3f and f2 is f, so 3f minus f, that is 2f, and in our case it is actually 2f, so the actual distance between both the lenses is 2f, so d actual is equal to d required is equal to d actual. Now we will determine the equivalent focal length. So the formula for equivalent focal length is written here, you can note it down. F is equal to f1 f2 upon f1 plus f2 minus d. So here in our case f1 is 3f and f2 is small f, so 3f into small f, 3f plus f minus 2f, d that is the distance of separation between the two lenses, that is 2f. So 3f into 3f, 3f square, and 3f plus f 4f minus 2f upon 2f. So here 1 is f will cancel, so 3f upon 2, that is the equivalent focal length. So now I hope you understood the whole concept, and if you still have a doubt you can ask in the comment section. Thanks for watching. Subscribe my channel for more.